Friends, welcome to the 29th lecture on Advanced Steel Design course. In this lecture, we are going to learn how to derive the stability functions under axial compression. Friends, in the last lecture we discussed about the derivation of a stiffness method using stiffness method of a standard fixed beam, and we understood that a standard fixed beam has got 4 kinematic degrees of freedom as marked on the screen. We have used a specific sign convention that anti-clockwise moments and rotations are positive, displacements upward, shear and displacements upward are positive. Similarly, along x-axis, displacement and forces will be positive. We have used this sign convention and we have derived a stiffness matrix of 4 by 4. Obviously, we neglected axial deformation and we derive the stiffness matrix as you see on the screen. We have the labels P, Q, R, S, P, Q, R, S. These labels have a specific order. Please see this order. Rotation, if this is my jth end of the member, this is my kth end of the member, along the length of the member is my x-axis, y-axis is anti-clockwise 90 to x-axis. Therefore, the degrees of freedom are labeled in such a manner: rotation at jth end, rotation at kth end, displacement along positive y at jth end and displacement along positive y at kth end. So, P, Q, R, S, this is the order. So, we have written this order here and we know this is going to be KPP. K represents the element of this matrix, KPQ, KPR, KPS, KQP, KQQ, KQR, KQS, KRP, KRQ, KRR, KRS, KSP, KSQ, KSR, KSS. While writing this subscripts of these elements of the stiffness matrix, the first subscript refers the row and second subscript refers the column. That is a standard practice what we do in representing the equations or mathematical formulae in a matrix form. Okay. So, this is a 4 by 4 matrix. Yesterday we learnt that these 4 coefficients are named as rotation coefficients and these 4 coefficients are termed as translational coefficients. And we derived this, the remaining coefficients, as a function of this, is it not? For example, I am just revising. KRP is sum of these two by L. So, I can say KPP plus KQP by L and so on and so forth. So, we have got all the 16 coefficients learnt and understood for a standard fixed beam, neglecting axial deformation. Is it not? Having said this, we will follow the same analogy but now we will derive the stability functions under axial compression. It means I am going to apply an axial compressive force to the same fixed beam module and derive the matrix in the same order as we have derived earlier. Okay, let us see how we are going to do that. So, now I am going to say, consider a beam element, both ends fixed. Okay, let us consider this element. This is my element. And let us mark the axis. We know this is my x axis. My y axis measured anti-clockwise 90. And this A and E is considered to be constant along the length of the member. It is a prismatic section. Okay. So, let us mark the degrees of freedom for this. They are all restrained. Let us mark them in red color. Okay. So, this is theta p, this is theta q, and this we know is del r, and this we know is del s. There is no confusion in this, isn't it? It is very clear. In addition to this, I am going to apply an axial force P A at both the ends. Okay, let me mark this xm slightly in a different color so that it does not get confused. This is ym, let me also mark this ym here. This xm, m represents the member, okay, and this is my force which is axial. Okay. So, there is no confusion in this, and the length of the member is Li, let us say it is an ith member, okay, it is an ith member, and we know that this is my jth end, this is my kth end, okay, that is how we have marked. Now, this is the figure of a fixed beam under axial compressive load. Friends, please understand, when you derive the stiffness matrix, there was no load applied. Stiffness matrix is of course independent of any load, okay. But now in this case, I am going to derive the stability function. Therefore, we already learned stability is that function or that capacity or that ability of the structure to perform its intended function up to the critical load for which it is designed. Okay. So, I am applying the axial load which is in compression, right. I am going to compress this beam from either ends. Please note very carefully here, friends, very carefully. The element or the module does not have axial degree of freedom. The axial degree of freedom is neglected. Please note that. I have only 4 degrees of freedom, P, Q, R, S, right. Similarly, what we had in the fixed, there is no change in that. Having said this, let us now derive what is called rotation functions. As earlier we derived what is called rotational coefficients, now I am talking about stability function. Therefore, I have rotation functions. Okay. So, now to get this rotation function, I must apply a unit rotation. Let us see that. I am taking the beam, fixed both the ends. The beam is now subjected to an unit rotation theta p. So, it is the same algorithm what we did in the beam earlier. That is why I explained the beam analysis first. Okay. Now, let us mark the axial force present in the section, is it not? This was new. In the earlier beam analysis, this was not there. Let us also mark the degrees of freedom. Let us say, okay, I will not mark the degrees, I will mark the forces. So, what I am going to do here is, I am going to say this is my force KPP, this is my force KQP, and this is KRP, and this is K. Okay, let us write this KQP here, let us write this KPP here, let us mark exactly this here. So, KRP and KSP. What are these K, RP, SP, etc.? They are all forces when the system is subjected to unit displacement. So, they are actually similar to stiffness coefficients. Okay. Can also put a superscript I saying that this is for the ith member, but that is redundant. I mean, it may cause additional confusion, so I am avoiding that. Okay. And of course, we know this is the length of the member Li. Right. So, now this figure indicates unit rotation at jth end of the fixed beam, am I right? Subjected to axial compression, correct? Okay. So, now when you do this, this will start developing moments and shear at both ends of the member, both j and kth ends, is it not? So, now this has an unbalanced moment anticlockwise, which will be KPP plus KQP, am I right? So, can I now say KRP will be actually equal to this unbalanced moment by L or Li, because that is going to form a couple. When I say this is a couple, so this will be upward, this will be downward. So, can I say now KSP is same as KRP, but with a negative sign. So, I will call this equation as 1. I hope there is no confusion at this stage, is it not? The same identical analysis what we discussed for the fixed beam. I am just following the same algorithm, so it is easy for us to do it. Now, what I do, I draw a free body diagram under the influence of this by cutting a section somewhere here, let us see, and draw a free body diagram. Let me do that. I draw a free body diagram, a fixed beam, one end fixed. I have applied a rotation and I drawn a tangent, and this is unity. It is subjected to an axial force Pa. It is having end moment KPP, because free body diagram is a true representation of all the internal and external forces acting on the segment considered. So, this is going to be KRP. Okay. Now, at this stage, I have a balanced force PA to counteract this. Let us say that is at a distance y from the axis of the member, and it also has a moment which is m. I should say this figure represents free body diagram under axial compression and unit rotation at jth end. Can I say that? Right. Now, we also have the classical differential equation to represent this, okay, which we discussed. So, I will copy this figure or write it here itself. So, now I say with reference to this figure free body diagram, I can say EI into d square y by dx square is m. And this m is minus PA into y, okay, minus PA into y minus KPP plus KRP into x. Okay, I am considering a section at a distance x from here. Okay. So, now let me expand this equation. EI d square y by dx square is minus PA into y minus KPP plus KRP into x. Now, we already know from equation 1, I will call this equation number 2. From equation 1, we know KRP is expressed as this. So, substituting from 1, 2 will now become EI d square y by dx square is minus PA into y minus KPP plus KPP plus KQP by Li into x. Can I say this is equation number 3? I have just substituted, okay. So, let me rewrite this equation, rewriting equation 3. EI d square y by dx square is minus PA into y minus KPP plus KPP plus KQP by Li into x. Equation 3, same equation I have rewritten. In the above equation, let us express the axial load, that is PA, as a function of Euler load PE. You may ask me a question, why are you doing this? Because answer is we are aiming to derive the stability function. Stability function is related to Euler's load. So, therefore, let PA be expressed as some function of P. Call this equation number 4. Okay. We already know that PE is pi square EI by L square for n equals 1. Hence, PA will be pi square phi I EI by Li square for n equals 1. Can I have this as equation number 5? Okay. So, friends, there is a very important observation we want to make here. Please note that buckling is occurring in the plane where unit rotation is applied. You may ask me a question, suddenly how I have introduced the term buckling? Friends, look at this figure. This is a beam or a column element subjected to axial compression. Under axial compression, column will buckle, and that is one of the failure mode. We already discussed that in the previous lecture in detail, isn't it? So, I will not no more call this as bending. This is not happening because of any lateral load or gravity load. The profile what is shown on the screen is happening purely because of buckling, and it is happening on the same plane where unit rotation is given. Is that okay? Then you may ask me a question, sir, why we are estimating buckling when rotation is given? That is very good. We are estimating that load which is going to cause failure. So, we are expressing that load of PA as a function of Euler's load. If that load PA exceeds Euler's load, it will fail, and that failure will be called as buckling failure. That is what Euler stated, is it not? So, I am using the same logic, I am expressing it. Okay? So, therefore, I am calling this as buckling, and let us remember that this is happening on the same plane where unit rotation is applied. What is this plane? To be very clear, it is XM YM plane. Is it not? See here, it is, this is XM and this is YM. That is the board, is it not? It is happening on the same plane, right? Therefore, let us modify equation 3 in this understanding, okay, because we have substituted, we have got PA in equation 3, PA is expressed in a different form in equation 5. So, let us substitute equation 5 and update equation 3. So, let us update equation 3 after substitution. So, that becomes EI d square y by dx square is going to be minus pi square phi I EI by Li square of y minus KPP plus KPP plus KQP by Li of x. We call this equation as 6. Okay. Now, I will divide this equation 6 by EI and rearrange the terms. Divide equation 6 by EI and rearrange the terms. Let us do that. So, if I do that, I will get this equation now, which is d square y by dx square is equal to minus pi square phi I by Li square of y minus 1 by Ei of kpp plus 1 by Ei of kpp plus kqp by Li. Let me rearrange it further. D square y by dx square plus pi square phi I by Li square into y is equal to 1 by Ei of kpp kqp by Li or into x by Li minus kpp. We will call this as equation 7a and this as 7b. Now, look at this equation 7b. It is a second order differential equation where right hand side is not equal to 0. So, this will have two solutions. One is a complementary function, other is the particular integral. So, the solution of equation 7b will have two components. Namely, complementary function and particular solution. This is a standard procedure which you will have described well in many mathematics books on differential equations. So, we will not cover that discussion at this moment in this lecture, but I request you to go through additionally some material to learn this. Okay? So, therefore, now the solution y will be equal to a sin alpha I x by Li plus b cos alpha I x by Li. This is the complementary function. Then the particular solution comes plus Li square by alpha I square Ei of kpp plus kqp into x by Li minus kpp we will call this equation number 8. This is a standard solution which can be easily understood from ordinary differential equation textbooks. Okay. We will also say where alpha I, which is introduced here in the above equation, is pi times of root phi I. Phi I already is here, okay, we have defined that here. Is actually the number or the ratio between the axial force applied and the Euler's law, okay, that is what we have said in equation 4. Okay, we will call this as 8a for example, this is 8b for our understanding. Now, this equation 8a has got two differential equation coefficients, that is a and b. We need to find them. So, obviously we need to apply the boundary conditions. Let us apply the boundary condition. First boundary condition, at x equals 0, y is 0, okay, that is what it is. See this figure, at x equals 0, y is 0, is it not? That is this point. So, if I apply that condition, we get B, because this term go away, this term becomes unity, okay, this term goes away and you get this, which is negative. So, can I say B is going to be equal to Li square by alpha I square Ei of KPP? Can I say that? Okay. Let us apply the second boundary condition. What is that condition? At x is equal to L, again y is 0. See the original beam. At x is equal to L, that is here, again y is 0, is it not? So, let us apply that condition here. So, if I apply that condition, we will get 0 equals A sin alpha I plus B cos alpha I. So, KPP gets cancelled, okay. So, I will get plus Li square by alpha I square Ei of KQP, is it not? Because Li and Xi gets cancelled because x is equal to L is the condition. This is what I get. We already have the value for B, okay. Let us substitute that here. Now, substituting for B and simplifying, minus Li square by alpha I square Ei of KQP will be equal to A sin alpha I plus B cos alpha I, which means minus Li square by alpha I square Ei of KQP minus B cos alpha I is A sin alpha I, which means minus Li square alpha I square Ei KQP. B is Li square KPP. Okay, let us do this. So, minus Li square by alpha I square Ei of KPP of cos alpha I, which is A sin alpha I. Am I right? We will name these equations. We will call this as 9A, this as 9B, this as 9C, this as 9D. Okay. So, now I can say minus Li square by alpha I square Ei of, oh, there is KQP here, KQP plus KPP cos alpha I divided by sin alpha I is A. Can I say that? So, which means minus Li square by alpha I square Ei K QP cosecant alpha I plus, right, KPP cot alpha I is A. So, let me call this as 9F. So, I have the value for A, I have the value for B also. See, B is available here, A is available here. So, substituting for A and B in the original solution, we get, what do we get? Please check that, what do we get? Where is the original solution? This is the original solution I have, okay, this is the original solution I have. So, let us rearrange the terms, okay, let us again, we can even copy this, let us try to copy this. Okay. Let us remove this marking. Remove the number also. Okay, which is equal to alpha I, because you know A has a multiplier alpha I square. Okay. If you look at B, it also has a multiplier. Okay, and this term also has a multiplier. So, if I keep all this common out and take it to the left hand side, this will become alpha I square Ei by Li square of Y, which will become minus KPP cot alpha I plus KQP cosecant alpha I of sin alpha I x by Li, that is my A, plus KPP cos alpha I x by Li, that is my B. Okay. And we have one more term, which is this. Okay. Let us enter that, plus KPP plus KQP into x by Li minus KPP. This is equation number 10. I think we all agree that equation 10 is easily derivable for our understanding. This is for y. I can differentiate this once to get dy by dx. Okay. Differentiating with respect to x, equation 10, we get alpha I square ei by Li square of dy by dx is equal to minus of alpha I by Li kpp cot alpha I plus kqp cosecant alpha I of cos alpha ix by Li. That is the first term we get, minus alpha I by Li of kpp sin alpha ix by Li. That is the second term we get. We get one more term, which is kpp plus kqp into 1 by Li. Equation 11. So, we have two equations now for the displacement and for the slope, dy by dx the slope, isn't it? So, let us rearrange this term, this equation in a closed form, which will now become alpha I square ei by Li square dy by dx will be equal to, because there are many kpp terms, let us group them all. So, kpp term here, there is a kpp term here and pp term here as well. Let us group them, which will become kpp times of 1 minus alpha I, okay, 1 minus alpha I let us say this is Li. I am cancelling Li square and Li because there is an Li here and there is an Li here. Okay. So, Li 1 minus alpha I, 1 is this, minus alpha I sin times of alpha ix by Li, which is this term, okay, minus alpha I times of cot alpha I of cos alpha x by Li. That is my kpp. Let us talk about kqp plus kqp of 1 minus cosecant alpha I into cos alpha x by Li. You may wonder why we are arranging the equation 11 in this order. Please understand, I want to obtain k, pp and qp ultimately. That is how we already derive the rotation coefficients for the fixed beam when we do the stiffness analysis, is it not? So, we want to group it in that order. We are trying to do that. Let us call this as equation 11a, because equation 11 and 11a are only rearranging of terms with some simplification. Okay. So, friends, we look at the summary what we discussed in this lecture. In this lecture, we are learning to derive the stability function for beam under axial compression. We have followed identically the same procedure with which we derive the stiffness matrix of a fixed beam. But in this case, we applied axial compressive force Pa and deriving the stability function. So, while doing so, we made a simplification of expressing this Pa as a function of Euler law. Why we did that? Because we wanted to assess stability, and Euler's law will help you to give stability, because I can quickly compare Pa with Pe and say whether the member is stable or unstable. We already learnt it in the previous lecture, how to define stability in Euler's criterion. Okay? Therefore, we are trying to use this relationship and derive the stability functions. We will continue this derivation and do these stability functions in the coming lectures. Thank you. Have a good day.